In this unit, we will explain about pattern or string matching methods. The pattern matching or string matching are very much widely used in applications such as spam filters designing, parsers development, digital libraries, genome matching, file searching, word processors, web search engines, natural language processing, screen scrapers, and feature extraction in digital images, etc. There are many methods are available for pattern matching applications or string matching applications. We will be first discussing a method we call it as a brute force method. It's a crude method of searching for a string in a string. It is not efficient technique. Here, every possible location is selected from the input string and searched for the search string. The complexity of this problem is proportional to the size of both the strings. The input string length is m and the pattern to be searched is n. Then the order of the complexity of this method, brute force method, is order of mn. For example, let us consider that we are interested to find out the string needle is seen in the given string or not. So we will take a substring starting from h, which is of length needle, that is 6 characters. Then try to match these characters of the substring with the needle. If they are not matching, of course in this example they are not matching, then we will take element starting from a, the next element onwards, and then compare with the needle. Like this we will proceed till we get the solution or till there are no more substrings to be compared in the input string. The program for this application is shown in this slide. We consider x is the input string in which we are interested to search whether the string y is available or not, that is embedded or not. We assume the length of the string x as n, the length of the string y which is required to be searched is m. Then, as we have already mentioned, we are supposed to take substrings of the string x of size string length y, that is m. So how many substrings from x we can select which are of length m, that is n minus m plus 1. Thus we have taken k as n minus m plus 1, and then we will search for the matching for each possible substring of the array x. The following slides will demonstrate how this code works. Consider the strings are, that is x is Ramachandra and the string y as Chand. The string length of x, that is 11, string length of y, that is 5. Thus n value is taken as 11, m value as 5. Thus number of substrings from x of length 5 becomes 7, that is k value becomes 7. Now when I value becomes 0, we are supposed to take a substring of length 5 from the string x starting from index 0. And then each of them will be compared with the contents or characters of the y. That is taken care by the inner for loop. x of I plus j is R, yj, j value is 0, yj is C. They are not same, which indicates that the string Chand is not seen from the original string x starting from location 0, that is I value 0. From that onwards, the 5 characters we have taken, they are not same as Chand. Thus, we'll shift by 1 character, that is I value will becomes 1, and then searching will be carried out. That is, we'll take this time a substring starting of length 5 characters starting from element 1. Thus, we'll be continuing the search. Now, we are trying to check for the matching of the substring starting from 1 in the original string x. X of I plus j, that is a, y of j, y of 0, that is the 0th character of the y, and what you call x of 1, that is a, they are matched. They are compared. They are not same, which means that Chand is not seen starting from the element 1 of the string x. Thus we will skip and then we will continue the next location in the string x. Like this, when we verify that the substring starting from 2 and also starting from 3, they are not same as the Chand. Now we have taken I value as 4. That is, we are trying to consider a substring starting from 4th element of the string. Now x of I plus j, that is C, y of j, that is also C. They are same. Thus, j value will be incremented by 1. Now x of I plus j, that is h, y of j, that is y of 1, it is also h. They are same. Thus, j value will be incremented by 1. Now, again x of I plus j is a, y of j is also a. Thus, j value will be incremented by 1. Again x of I plus j, that is n, y of j is n, they are same. Thus, j will be further incremented by 1. Now again x of I plus j, that is d, y of j is d. They are same, which indicates now all the characters of the string y are same as the characters starting from 4th location in the input string x, which means that now the string Chand is seen in the string Ramachandra. Thus, the program says found. The worst case behavior of this algorithm occurs when the two strings are as shown in the figure. That is, the first string, that is the string x, or in which we want to search for a string, is of the form all is b followed by b, whereas the second string is of the form shown in the things. Then only this algorithm will have worst case behavior, whose order will be proportional to mn, where m is the length of the string to be searched and n is the length of the string in which searching has to be done. The following slides demonstrates how a brute force technique works with another example. In the following slides, we will try to demonstrate working of another algorithm which is popular, known as Boyce Moore algorithm. The main object of this algorithm is as follows. Before we talk about the algorithm, we are taking T as a string in which search has to be done. P is a string in which is supposed to be searched in T. This algorithm is based on two heuristics known as looking glass heuristics. That is, here it compares by moving in backward direction compared to forward direction of the previous method. Also, essentially, whenever it tries to compare at some location in the original string T, if a mismatch occurs at T of I, that currently T of I value is C, and if the string P contains C, then we will shift P to align last occurrence of C with Ti. Else, if there is what you call if P doesn't contain C at all, then shift P to align P0 with the T of I plus 1. That's how we will be skipping some characters in the original string T for our search purpose. This is the essence behind this technique. Let us try to explain this algorithm with some sample data. The string T is given and also the string P is given as RITHM. Now we try to match first time the string RITHM in the backwards we said already. So now the last character of the string P when it is aligned with the string T, that is M, and the respective character in the string T is lowercase t. They are not matching. Now we have to verify whether the string P contains T or not. Yes, lowercase t is available in the string P. So thus we have to see, we have to switch or rather shift by 2 units and then we have to continue the search operation. That is the essence here. And that is the step we are going to have. That's known as a jump characteristics of this. Now, when we shift the string P by 2 units, and then the respective character in the string T is E, lowercase e. Is lowercase e available in the string P? That is in RITHM string? No. Now what we are supposed to do? We will shift the string P by what you call length of the string P, 5 characters, and then searching will be carried out. Now this time the string P's last character is aligned with A as shown in the figure. That is A is of the string T. Now there is no match. Now we will check whether the character lowercase a is it available in the string P, that is RITHM? No. Thus we will shift the string P by that many characters towards right. Rather I say we try to align the 0th character of the string P with T of I plus 1. That is the one we are going to do. Here also, when you try to match the last character of the string P with T of I, that is N now, lowercase n, we find that there is no match. Then we will verify whether the N is available in the RITHM, the P string or not. As it is not there, again we will try to align the string P0, that is the character of the string 0, string P, that is the 0th character of the string P, with next character in the original string, that is with G. In this attempt also, no match, and also G is not seen in the string P. Thus, now again P is aligned with the next character of the string T. Here also there is no match. Thus, the string will be shifted by 1 unit. Rather, I say next 0th character of the string P will be now aligned with the next character. Now, if we verify that the last character of the string P is now matching with the respective character in T, then all the characters are matching. Thus, we can say the string is available in the given string T. Like this, unlike the brute force method, here we will be skipping some space, some characters, and then searching will be continued. Just for the sake of clarity, we have worked out another example. You can verify the same. Rather, I say how Boyce Moore algorithm works. We have traced out. You can verify yourself to feel of this algorithm. This algorithm pre-processes the pattern P and creates an array known as last, which contains, rather I say, which can be indexed by the numeric codes of the alphabets available in the string, and contains the last occurrence information about the alphabet in the given string P. If the alphabet is not available, then the respective element contains -1. Let us take, for example, the alphabet is ABCD. The given string is ABACAB. Thus, the last function when it is calculated, last of x. If x value is A, its value is 4. If it is B, 5, C, 3, D is -1. As D is not at all seen in the string ABACAB, that is P, the string P, we are taking D, last of D as -1. Now verify if the alphabet value is taken as C, that is x value is taken as C, last of C, that is 3. How that is available? The string is ABACAB, that is the location of C in the given string P is third location from the third location. Thus, C value will be taken as 3. Rather, I say from the last, it is 3. Sorry, from the beginning, if I consider 0th element, the index is 3. Similarly, if we take B, that is where it is available. The last occurrence of B, where it is available. The string is having 2 B's, but the last B is available where? In the 5th location. Thus, last of B is taken as 5. Similarly, A is seen in the given string ABACAB 3 times. The last A is available in the fourth location. Thus, last of x value will be taken as 4. Like this, the function, rather say an array last, which can be indexed by these symbols, can be calculated by the cost of order of m plus s, where m is the length of the string p and s is the number of alphabets. This function is used in Boyce Moore algorithm. The function, rather I say the Boyce Moore algorithm, can be carried out as above. We consider as usual the string t is a string in which we wanted to search for the string p, and we assume that their lengths are n and m respectively. Now we take an array. We assume that an array last contains the last occurrence information of the alphabets in the given string p. Now we take I value as m minus 1, j value is m minus 1. First that means we first time align the given string p with such a way that m minus 1th character of the string t will be same as m minus 1th character of the string p. The first m characters we try to take and compare. As we have already mentioned, we are going to compare from the backward direction in this Boyce Moore technique. So if t of I is not equal to is equal to p of I, and if j is equal to 0 means the string is available. Otherwise, what we do is we'll move backwards. That is t of I is equal to p of I. Then we'll reduce I and also we'll reduce j also by 1. Then we repeat this do while loop. So by chance, if j is equal to 0, which means that from this location m minus 1, all the characters are same. Then if it is so, we return the I value indicating that the string is available in the string. If t of I is not equal to p of j, so we take a variable L whose value will be taken, is considered as the last occurrence of that character t of I in the string p. So with that one we are supposed to match. In our previous explanations, examples, what we have done, we find out where is the character t of I in the given string. If it is not available, we simply align with the t of I plus 1. Otherwise, we will skip that many things. So that is being done by calculating the last or using the last function. I is taken as I plus m, minimum of j or 1 plus L. So we will skip that many characters. As long as I is greater than n minus 1, we repeat. So if we come out from this do while loop, then we return minus 1 to indicate that the string p is not seen in the given string t. Now consider the situation case 1 as shown in the above figure. Currently I value is pointing or is the index of a character A in the given string T, and J is the given string P pointing to a character B. There is a mismatch. Now mismatch is occurred. Now we are interested to find out in the given string A is available, given string P, this mismatched character A is available or not. Incidentally, it is available. The last occurrence of this character A, when you find out last with the help of last function for this data, this becomes 5. What is the value of J? It is 4. So, which means that it is the character last occurrence of A is the right hand side of the character B. So that's the reason why we have to align now the last occurrence with the T of I. For this, we have to shift the string m minus j units. Similarly, case 2 also, if you verify, when the mismatch occurs, T of I value is A and P of j value is B, and if I assume that first occurrence of A from the last is at location 1 in the string P, then we have to shift the string P by some number of cells, some number of units, such a way that this A in the string P will align with the A of the given string T. Like this, the I value will be updated. Once after alignment is done, then J value will be made as m minus 1, such that again searching or matching will be done from the end of the given string P. Like this algorithm works. The following slides will explain how this algorithm practically works on a simple data. We understood that when we align first time the string example, it is aligning with the character S. We found that S is not at all seen in the string example. Thus, according to our algorithm, we have to shift the matching by that many characters, that is equal to the string length. Rather, we have to align the string now with I plus 1, that is P of 0 should be same as T of I plus 1. However, for the sake of explanation, we are taking an imaginary character S is added to the string. So from that onwards, the S example, that is the string we are trying to align with the string T. Now, the last character of the string P, that is in our case example, is now aligned with the character P of the string T. Now we'll try to see whether the P is available in the given string. Yes, P is available in the given string. That's also from 2 units from the last character. Thus, we'll shift matching by 2 characters. Now, the characters of the string P are having matching until the last four characters. That is, E is matching, L is matching, P is matching, then M is matching. But however, now A is not matching. Now a respective element in the string T is I character. So now is I available in the string example? No. Thus we have to shift the character or a string P such a way that P0 will be next to the character I, that is T of I plus 1. When we align the string, the respective element in the string T is P. Is P available in the given string example? Yes. How far it is available? 2 characters from the end. So thus now we'll shift the P string P by 2 units to the right. Now the string is aligned as shown above in the slide. Then when you compare the characters, we may find the characters of the string example will be matching with the respective elements in the string T. Thus matching is found. That is, the string example is available in the string T. Like this algorithm applies some character jumps, and then it will be testing whether the string is seen in the given string or not. Compared to brute force algorithm, this is efficient as it is not going to check all the locations. It is going to omit some locations in the given string and continues the search. Thus, the computational advantage is better. In the following slides, we'll demonstrate how another popular pattern matching technique known as Knuth-Morris-Pratt algorithm. This algorithm first pre-processes the pattern P to find matches of prefixes of the pattern with the pattern itself. That is, it uses a special function, rather it calculates a special function known as fail. The function fail of I is defined as the size of the largest prefix of the string starting from 0th character to jth character, that is also a suffix of the string P starting from first character to jth character. We'll demonstrate little later how this fail function will be calculated. After this fail function is calculated, this algorithm modifies the brute force method so that if a mismatch occurs at a location P of j not equal to T of I, that is rather at a location I, we set the j value as fail of j minus 1. This is the concept is used. Let us try to understand how to calculate fail function. Let us consider j value is 2. Then the definition says fail of j is the size of the largest prefix of 0 to j and which is largest suffix of 1 to j. First of all, what are the suffixes of the string till the element 2? They are ABA, AB and A. What are the suffixes of the string starting from 1 to j? That is BA and A. Out of these things, the largest suffix which is same as prefix is A. Thus, the fail function value for 2, j value 2 is 1. Now consider the fail function calculation for j value 4. The string until j is AB, AAB. What are the prefixes for this? AB, AAB, AB, AA, ABA, ABA. What are the suffixes of the string starting from character whose index is 1 to till j? That is, we are supposed to calculate the suffixes for the string BAAB. What are those things? BAAB, AAB, AB and B. So, if we verify AB is the largest prefix of the string 0 to j, which is suffix of the string 1 to j. Thus, fail value becomes, for this j value 4 is 2. The main theme behind this algorithm is as follows. Let us take a situation that in the string P, that is the one which we are trying to search in the string T. So usually we take the outer loop to traverse the string T. The inner loop will traverse the string P. So in this case we are taking the loop control variable as j. So at some value of j as shown in the figure, incidentally j value is now currently, that is the 5th character. The respective character in the original string, the input string is x. There is a mismatch. Now, if we verify that the characters before x, there are some characters like AB, they are matching in the string P. So, we wanted to have an intelligent jump instead of brute force technique, in which the search carried out by shifting the I value by one character will search. We will continue the search. But we do not want, we wanted an intelligent search. In this algorithm, we follow this. If we verify the string P, rather I say the characters of the string P before j, they are AB, AAB. So, if we verify, rather I say, we are having a small pattern. The largest string starting in the original string P, which is having, that is the prefix of the string AB, AAB, largest prefix, which is having same as largest suffix is AB is available at the beginning, and at the same time AB is available at the end. So, which means that instead of simply jumping to the next character and continue the search, already we know that those AB characters are having match. So we adjust J value such a way that J value will be set to J minus 1, fail J minus 1. So currently J value is 5. Then we make J value as fail J minus 1, means if we verify the fail table, it is 3. So which means that now we will continue the search as making the J value as 3. This is the essence behind this technique. The basic concept behind this algorithm is as follows. When a mismatch occurs at some location, say I, that is, the string P is aligned at location I in the original string T. And we found that at the jth location of the string P, there is a mismatch. By this time, we might have spent some computations, or these comparisons. We have some knowledge of characters T of I plus 1, etc. till T of I plus J minus 1. This algorithm tries to use that knowledge and decides whether to skip possibly some locations of I from the normal brute force technique or not, such that the algorithm becomes efficient. For example, consider the following two strings T and P. Consider I value is 2, that is second element of the string T. From there onwards, we are trying to continue our match. We found that the first character of the string P is n, then T of 2, as I value is 2, T of 2 is also n. When then the next character is also matching, that next character is also matching. However, when J value is equal to 3, that is third character of the second string P, that is 0, the respective character in the string T is lowercase a. They are not matching. Now, in the next next attempt, we will be making I value to 3. Then we will be skipping one character and then continue the match. But however, we know the T3 value is A and T4 value is N. If we verify the string J, P, the first character of it is N, second character it is A. Thus, definitely there will not be match in the next attempt, as T3 and T4 are AN, whereas the respective two characters in the string P are NA. There will not be any match. Thus, we need not require to continue the iteration for I value is equal to 3. Then which is the best trial? So if we verify that when you start from the next iteration, it is a 4, so T4 value is N, and the first character in the P is N. Thus, that is these two N's are coinciding. Thus, we can search or continue our search for I is equal to 4 onwards. Consider another example for the sake of understanding. The strings T and P are as given above. When I value is equal to 0 and J value is 3, we found that there is a mismatch. If you observe, we know that the string T, T1 is B, T2 is C. They are not A, capital S. That is the first character of the string P, P0s. That is the reason why definitely we need not require to check starting from I value is 1 and I value is 2. Even I value is 3 is also not required. Why? They are not same as P0. Definitely the string will not be there starting from that values of I, that is I is equal to 1, I is equal to 2, I is equal to 3. Thus, the search can be continued from the I value is equal to 4 and setting J value as 0. Now, if we assume that the search is continued from I is equal to 4 and J value is initialized to 0 initially, and then when we verify, when J value is equal to 6, there is a mismatch. That is, the respective character in the string T is a space, and whereas the sixth element in the string P is D, symbol capital D. So thus a mismatch is occurred. However, now this algorithm, KMP algorithm, works in this fashion. So if you verify the characters of the string T before the mismatching character, they are A, B, C, D, A, B. So now the largest prefix of this one, which is having a suffix of this one, which is having same prefix of the string P0. String P is AB. That is, when we try for, let us assume that when we try for I is equal to 5 onwards, what is the character at T5B? What is the respective character P0 in string PA? Definitely they are not matching. Even the second I is equal to 6, there that is a C, and whereas this is A, not matching. When we try for I is equal to 7, that is D, will not be matching. 8 also will not be matching. However, when I value is equal to 9, we may find that the character in the string T is A and P0 is A. Similarly, T10 is B, then P1 is B. So that's how we can continue our search from I is equal to 8 onwards. And we already said that AB, that is T8, T9, they are ABs, and P0, P1, they are ABs. So already they are matching. So that is the reason why we can set I is equal to 8 and j is equal to 2 we can set. Then we can continue the search. Like this, here essentially we'll try to find out whether there any way of eliminating some of the searches in brute force technique and get the matching in the fastest possible manner. This algorithm gives worst case behavior in the following type of situation. We do have another type of searching method, string matching method, known as KPM method, with deterministic finite automata. First, we will construct a deterministic finite automata from the string P, and then we evaluate by presenting the string pattern T and see whether we reach the acceptable state, the final state in the DFA or not. I'm sure most of you knows how a deterministic finite automata can be constructed from the given string with some number of alphabets. However, the following slides will explain how a deterministic finite automata can be first constructed for a given string P, and then how a given string T can be decided whether it is having P or not. The search pattern is given in the slide AABA, AABB. Thus we may verify or we may understand that it contains two alphabets A and B. Thus we have to design first DFA diagram for this pattern P. As usual, we assume that 0 is the initial state of the DFA. When the alphabet A arrives, we assume that its state is changing to state 1. If the alphabet B comes, the state will be in the same state, 0. When we are in the state A1, when alphabet A arrives, we assume that the state of the DFA changes to 2. If B arrives, the state will come back to 0. When we are in the state 2, any series of A's, alphabet A's arrives, the state will be in the same state. If alphabet B arrives, the state of the diagram, the DFA, will be assumed to be changing to 3. Like this, using our knowledge of discrete mathematics or automata theory, we can define or we can find out the DFA for the given string P. The following slides will demonstrate how DFA will be calculated for the given string P. Now, the given string T is A, B, A, B, A, B. Thus, first character A, when we present, state will be changing to 1. Next character again when we present, that is A, state will be changing to 2. Then again when you present A, the state will be in the same state, 2 only. Now the third index character is B, that the state will be changing to 3. That next character is A, thus the state will be changing to 4. The next character is A, thus state will be changing to 5. That next character is B, the state will again return back to 3. Now that next character is A, the state will go to 4. Now that next character is A, the state will go to 5 again. Now that next character is A, the now state will go to 6th state, which is state 6, which is acceptable state. Thus we can say that the given string text t, the variable t, the string variable t is having the given string p. Like this, we can use DFA to find out whether a string is available in another string or not. In essence, here first we have to design DFA for the string p, and then we have to present the string t and check up whether p is there in it or not. These are some of the methods which are